There. Okay. Okay, so I'm going to talk about some of the fractional topology.
No, you need to have your microphone on.
I have my microphone.
Okay, good. Fine.
There seems to be an echo. Okay, here. Okay, great. Okay, so today I'm going to talk about some of the interesting phenomena from the.
There was a question about microphone. Did you want to have a microphone for? How is the audio?
They can't hear at the back.
Yeah.
So
sorry.
Can you hear me?
You're speaking loudly enough. You're good. But
yeah.
The speakers are a bit quiet at the back.
Okay, so we could proceed without a microphone.
Okay, great. Yeah, so I'm going to talk about some of the interesting phenomena from about topological or fractional states arising from Murray lattices. So Murray lattices requires no introduction. But as for why Murray system is interesting, for this question, that if you ask 1,000 physicists, you probably will get 1,000 different answers. And this morning we already hear some very nice answer from Ali. Oh, why there is something covering the? Let me see if I can. Oh, here. Sorry. Oops, where's my? Oh, here. Okay. What's that?
The X on that as well.
It's hard. It's hard. Oh, no. Okay, great. Yes. Okay, so why Murray systems are interesting. So before I discuss the physics, let me give a brief my answer to this question purely from a series point of view. Okay. So let's look at this 2D phase diagram of physics problems. The horizontal axis is how difficult the system is. The left extreme says that the system is very easy. We know the exact answer. We know everything what's going on there. Okay. The opposite regime means the system is very complicated, very difficult to handle. Even if we use the most cutting edge theoretical, numerical, experimental tool, we still cannot figure out what's going on in the system. Vertical axis measures how complicated, how exotic the system is. The bottom part means the system is very trivial, not interesting at all. The top part means the phenomenon is extremely exotic and is totally against our intuition. Okay, so for physicists as a series, our dream world will be in the second quadrant. Okay, so they don't, how nice it will be if all the physics problem in our universe is very simple. We all know the exact answer, but on top of that, this exact solutions give us some exotic physics, not something trivial. That will be the dream world. Okay, but unfortunately, that's not how our universe works. Our universe is
difficult and exotic orthogonal concepts.
Okay. Yes. So unfortunately, most of the cases, our universe works in this way in the first and the third quadrant. We have plenty of systems which is extremely simple, and we know the answer, but in many cases, they give us some trivial phenomena. We also have systems of materials which we believe, very likely will have very exotic physics, but unfortunately, those systems are often very complicated, very hard to handle. We don't really know what's going on here. Okay, and the reason, and this from my point of view, I want to study the Murray system is because, as I want to demonstrate and want to convince you today, that the Murray flat band systems offer us an opportunity so that we can get some realistic physics systems, either in this ideal dream world, or at least it's close enough to this ideal dream world, so that we can do something. Okay, and that is actually extremely important for theorists because if we have something in this ideal dream world, it's dramatically improve our prediction power. It means that we can predict what type of exotic correlated phenomenon could appear in these systems, and we can even maybe be able to pinpoint the candidate material or this exotic state will arise in this particular material. Okay. So to demonstrate the Murray flat band give us this simple and exotic limit, let's first look at twist barrier graphene. And more precisely, let's look at the chiral limits of twist barrier graphene. Okay? Graphene or twist barrier graphene do not have the chiral symmetry, but we can take approximation to make it have the chiral symmetry. Chiral symmetry basically means some operator is anti-commute to this function. For graphene or twist barrier graphene, what we can do is this, because in graphene or twist barrier graphene, we have two sublattices, A and B, labeled with different color. If we allow electrons only tunnel between A and B sides, and turn off any tunneling from A to A and B to B, then the system has chiral symmetry. Okay, if in twist barrier graphene, this is so-called chiral limit. And chiral limit, of course, is not the real physical system, but if we can take approximation and approximately treat the system as a chiral limit, then almost everything becomes exactly solvable. For example, the band structure is exactly solvable because in the chiral limit, we know that by tuning the twisting angle, we can go to the magic angle, and this magic angle, the band become exact flat. So dispersion is exactly solvable. It's just energy equals 0, independent of k. And this flat band is also topological. It carries Chen number, and it's also a fragile topological band. And on top of that, quantum wave function can also be solved analytically. It's just some complex analytic function of x plus I1 and xy is our 2D coordinate. Okay? And more importantly, even if we turn on interactions, even after we turn on interactions, the exact solutions still exist. For example, in this chiral limit, if we turn on repulsive interaction and set our filling to be on some integer fillings, then we can exactly solve the ground state wave function. And the ground state wave function gives us some interaction-induced insulators. Depending on the filling, this insulator could be topological. If it's odd filling, then it's topological. If it's even filling, then it's topologically trivial. And on top of that, in addition to ground state, excitations can also be exactly solved. One can analytically solve for the Green's function in these systems, and the Green's function is just only free fermions, so it's no damping. Okay? That's what happened at 0 temperature. But if we go to finite temperature, unfortunately, this exact solution do not exist anymore. But at finite temperature for these flat band systems, it turns out we can do quantum Monte Carlo simulations. Okay, so typically for correlated electron systems, doing quantum simulation is actually very, very hard because typically the computational cost scales exponentially with system size. But for this flat band system, we prove that for repulsive interaction and integer filling, then if you use quantum Monte Carlo algorithm to try to simulate the system, then the system either has no sign problem or the so-called polynomial sign problem. It basically means that we can simulate the system, but the computational cost scales as a power law function of system size, which means that we can simulate very large system size and arbitrary temperature with very good accuracy with very high efficiency. Okay. And if we flip the sign of the interaction, make the interaction attractive, then again, exact solutions exist at 0 temperature. Here for attractive interactions, it doesn't really matter whether it's short range or long range. And to make things even better, if we flip the sign and make interaction attractive, the filling actually can be arbitrary. We don't need the integer filling anymore. For any filling, we can do this. We can find the exact solutions. And the exact solution is actually very simple. The exact solution for the ground state is just a BCS wave function. And for excitations, it's just a Bogoliubov quasi-particle theory. Okay? So BCS theory and the Bogoliubov quasi-particle theory, typically for a superconductor, it's a mean field approximation. But in this flat band limit, regardless of the filling, regardless whether we have short range attraction or long range attraction, BCS theory and Bogoliubov quasi-particle theory become the exact solution. See? That's what happened at 0 temperature. And again, we can go to finite temperature. And for finite temperature, again, there's no exact solution anymore. But luckily, we can still do quantum Monte Carlo simulation here and arbitrary filling, and there is no sign problem, which means we can simulate the system with just the power law computational cost, and we can simulate really large system. And from this simulation, we can see there is a very nice superconducting dome. Okay, for quantum level simulation, we see a very nice superconducting dome. And similar as what Ali was pointed out this morning, if we measure the superconducting TC of this dome and compare with the 0 temperature gap is actually orders of magnitude larger than TC. That's actually pretty much qualitatively consistent with this what Ali showed.
The question is the cost slips down as space transition.
That's right. Yes, exactly.
So you can measure the stiffness. Is that
That's right. That's right. Yeah. So basically, we measure the correlation and they try to match the correlation with the KD transition power. Yeah, exactly. Yeah. And the most interesting physics here is actually not about superconducting dome itself. Is that if we go above the superconducting dome, the system actually don't melt into a metal. It melts into a pseudo gap state. Okay. And this is again very similar to what Ali pointed out this morning. If we do SDM above the superconducting temperature, we can still see the gap. And this pseudo gap is actually the same type of pseudo gap or same type of phenomenon as we have been discussing for several decades, like the pseudo gap in cuprates and other correlated superconductors. The only difference here is this pseudo gap phase comes from exact solution and exact numerical methods. We know exactly what's the origin of the pseudo gap phase. Okay, so that's for attractive interaction. Now let's go ahead. Sure.
You have for the stiffness, you have this geometric contribution for this table.
Oh, you mean from quantum geometry?
Yes.
Actually, this is quantum mechanical simulation. It includes everything.
No, but I understand. But in principle, I mean, from the if it were
You mean the mean field theory from
right,
like
when you say BCT equals 0, you can do BCS exactly.
That's right.
So in principle, it does make sense here, despite the fact that this is a flat band. I guess it does make sense to do BCS and then afterwards ask a sort of KT kind of question.
That is actually a great question. I didn't go into the detail. If we assume the band is exact flat, then there is actually no TC is actually 0. And this simulation actually assumes it's putting by hand a bandwidth, a small bandwidth in the system. So the point is that this TC is controlled by bandwidth, where the pseudo gap energy scale is controlled by interaction strength. It's totally different quantity. When band is flat enough, we will always see this separation of energy scale. TC is very low, but the gap and the pseudo gap scale is much larger. Yeah, sorry, I didn't have enough time to go into the detail, but yeah, exactly.
You can put the bandwidth back in without violating the exacts.
The exact solution will be gone, but the fundamental still have no sample. One can add the expression back.
But then that means that ultimately you do need dispersion of the.
That's right.
to get
That's right.
this.
That's right. That's right.
Contrary to this geometry claims, where essentially even without dispersions you get the.
That's right. So the geometrical limit is basically a mean field, density state, and on top of that, of course, one can argue that the geometrical limit could still get a finite TC if I include additional remote bands. So this simulation only included the flat band. Okay, okay, great. Yeah, but for this simulation, we indeed so that we have finite TC. That's a very important ingredient in the simulation. Okay, great. So now let's switch to repulsive interaction and fractional phase. For fractional failing and repulsive interaction, again, we know what's going to happen. We will see a fractional quantum anomalous Hall state, or also known as fractional chain oscillators. Basically, this state are the same state as fractional quantum Hall state we see in lambda levels and fractional failing, but they are realized without external magnetic field, without lambda levels. Okay. The reason we know that this fractional state will happen for this Marie flat band is because of old intuition we learned more than 10 years ago. So more than 10 years ago, myself and the coworkers and also other independent groups simultaneously considered one interesting question, and we simultaneously found the same answer. So basically, the question we asked at that time, about more than 10 years ago, was that is that possible to get a fractional quantum Hall effect without using magnetic field, without using lambda levels? And all these groups find the same answer. Answer is yes. It's kind of actually very easy to achieve that. The only thing we need to do is we need to replace lambda level with a nearly flat band, but this nearly flat band need to carry a Chern. In other words, lambda level is nothing but a pretty flat Chern band. So as long as we get pretty flat Chern bands, we'll get the same physics. And the lambda levels, if we give fractional failing to this flat Chern band and give repulsive interactions, we will see the same fractional states. And this has been verified in numerous different models of this states. Very frequently we see these fractional states. And for after this insight is obtained for like about 10 years, this remains as like a unicorn in the series level. No one believes this can be brought into the real world, but the discovery of Marie flat band gives actually a new twist to the story. It makes that it's hopeful that we can bring this to reality. This is because, as I mentioned earlier on, this twist barrier graphene, for example, it gives us flat band. And on top of that, this flat band has Chern number. That's exactly the right ingredient we need. Okay, so can we get to this fractional state in twist barrier graphene? Well, let me first give you the theory answer, then I'll tell you the reality. Okay, so theoretically, let's first take the chiral approximation I mentioned earlier, where everything is exactly solvable. If we take the chiral approximation and go to the chiral limit, then the answer is yes. This system definitely will give us fractional chain oscillator. The reason is because in the chiral limit, this Marie flat band is extremely similar to lambda. If we look at the non-interacting band structure, same at lambda level, this Marie flat band and the chiral limit has ideal quantum geometry. On top of that, the wave function is also very, very similar. The wave function is just a complex and analytic function, just like lambda levels. And to make things even better, when we turn on interactions, we can still see something here. So for this flat Chern bands, if we are in the chiral limit, then we can define the so-called pseudo potential. This pseudo potential is the same type of pseudo potential Haldane introduced for lambda levels. Because Haldane showed that if we have lambda levels and if the electron repulsion follows this pseudo potential instead of Coulomb potential, then fractional quantum Hall effect is the exact ground state of the height. And for this flat Chern bands, if we are in the chiral limit, now one can prove that we can also define pseudo potential. And if electron repulsion follow this pseudo potential, then again, this fractional topological state is the exact ground state of the Hamilton. Because of this exact knowledge, we know for sure that if we are in the chiral limit, this fractional state definitely will appear. Okay, but what about reality? In reality, unfortunately, it doesn't. Okay, for two reasons. First of all, the real trace value of graphene is not under chiral limit. And unfortunately, it's a little bit too far away from chiral limit. If the trace value of graphene can be like 30 or 40% more close to the chiral limit, then this fractional state will be the ground state. But because it's too far away, if I dump everything, if I dump the realistic material parameter into exact dilation, into numeric simulation, we'll find that the competing state, like charge density wave, is actually always kind of slightly lower energy than this topological state. So topological state is actually never favored in trace value by just trace value of graphene itself. Okay, and there is another small problem. The other small problem comes from the fact that trace value of graphene or graphene has very weak spin orbital coupling. Because of the weak spin orbital coupling, electron spins or hole or particle spins in graphene is pretty much Heisenberg's. For Heisenberg spin in 2D material, we know that there will be a lot of thermal fluctuations for Heisenberg spin. And this Heisenberg spin fluctuation will give us magnetic field fluctuation because spin actually generates magnetic field. As a result, this system will always have a bunch of magnetic fluctuations, but for fractional quantum Hall effects, magnetic fluctuation is bad. We want the magnetic field to be stable. Okay, so this fluctuation is another problem. And so, realistic graphene actually don't have this fractional state. But actually, answer was actually, a solution to this for these two problems was actually demonstrated a few years ago experimentally in this beautiful work from University and Pablo and Amir Jacobi's group. And basically, what they showed is that trace value of graphene don't have this fractional state, but we can get this fractional state by just turning on a little bit of external magnetic field, about 2 Tesla. Okay. This external magnetic field, about 2 Tesla, is not used to generate lambda waves. It is not lambda wave. This magnetic field do 2 things. First of all, if we apply magnetic field, spin will not fluctuate and it will align with spin. So it pins the spin fluctuation, get rid of magnetic fluctuations. And secondly, this magnetic field also modifies the block wave function of this flat band, block wave function a little bit. And turns out that this modification wave function changes the effective interaction. And it happens that it lowers energy for the fractional state and make it more competitive. And eventually it becomes the ground state of the system when the magnetic field is about 2 Tesla. Okay, so bottom line, for graphene, we can't get zero field fractional topological state, but we can get this fractional state until very small magnetic field, about 2 Tesla. Okay, but can we really get this system, this fractional state with absolutely zero magnetic field? Okay, we asked this question and we explored this question theoretically shortly before this experiment. Okay, and basically the question we asked ourselves is that what are the best material candidates that will give us this fractional state exactly on zero B field? Okay, and as I just mentioned, one reason graphene will not work is because graphene has very weak spin orbital coupling, so the spin fluctuation is huge. Okay, and to solve that problem, Jacobi's group used external magnetic field, but we don't want magnetic field. We want something else to get rid of spin fluctuation. If we don't use magnetic field, there is actually something else can easily get rid of the spin fluctuation. That is just choose a material which has Ising spin instead of Heisenberg spin. In other words, we want a material with larger spin orbital coupling so that there is magnetic isotropy, so spin is aligned. For Ising spin, it can only be up and down. The fluctuation will be much lower. Okay? And luckily, there is already a family of material, actually Ising spin, that's actually transition metal dicogenase. So transition metal dicogenase are 2D materials. It's a big family of 2D materials. It's kind of similar to graphene, but with 2 major differences. First of all, the rotational symmetry is 3-fold instead of 6-fold, which means the direct point in transition metal dicogenase is massive. It's gapped, not massless. And more importantly, transition metal dicogenase has large spin orbital coupling, and the spins there are Ising. That's exactly what we need. And to make things even better, back when we considered this question, people already know. In trace failure, transition metal dicogenase, they are flat bands, and this band can be topological. So this is a beautiful work from Anna McDonough's group. They calculated the Murray band structure for trace failure TMD material and showed it's indeed flat and has non-trivial channel. Okay. So although this TMD looks like quite promising, but back in 2021, a few years ago, transition metal dicogenase was not considered a good candidate for this fractional state for 3 reasons. Okay, the first reason is actually the band is not flat enough. If you look at this figure, we can see that the top band kind of looks flat, but the gap between the two bands is tiny. So from the previous study of fractional chain oscillators in the last 1 decade or so, we did numerous models, and in all those models, we need the gap to be large, and we need the gap to be much larger than the bandwidth. The gap needs to be at least 1 order of magnitude larger than the bandwidth to see this state. But in this model, in this band structure, as you can see, the bandwidth is kind of comparable with band gap. So the bandwidth is too large, band gap is too small. So if you just dump this band structure into the simulation, we are not getting fractional states. Okay, that's one major problem. The second problem is that the transition dichotomies don't have chiral limits, which means that we cannot go to a specific limit, special limit, saying that, oh, for sure, fractional state will appear. Okay? And the last problem about transition dichotomies is has much lower mobility. Low mobility means that even if we have this fractional state, disorder may actually kill us, make it impossible to observe. So back in 2021, transmetal dichotomies has some promising features, but was largely believed to be a bad system for this purpose. Okay.
But
Yes, go ahead.
RS is very large for these systems.
So, yes,
The interactions are very large.
that's right. Yes, yes.
So,
You mean the interaction is much larger than the band gap between the
yeah.
two bands? Yes, that is actually a good question. The mixing between these two chain bands with opposite chain number is different from lambda level hybridization. It's more dangerous because the chain number is opposite. However, from our earlier numerical studies, something still is still a mystery because we don't understand. So in our previous studies, we have multiple models. We have actually a few models, which is a two-band system, chain number plus one, chain number minus one. One of them is flat band, the other is not. Okay. And when we do numerical simulation, we include both bands, chain number plus and one minus one bands, and turn on interactions. And when we gradually increase interaction scales, at least in two models, we find that the fractional state actually survives, even if the interaction is much larger than the band gap between the two bands, even if the interband hybridization is huge. And actually, Donut did one simulation. She set the interaction strength to infinity. This still fractional state is a ground state. We still don't know why, but numerically, this was observed at least in two models where interaction, even if it's infinite, much larger than the band gap, there's huge hybridization between the bands. Fractional state still survives. Not true for all models, but it's true for many models.
Experimentally, the reason why TMD systems are turning out to be
Oh, that's yes, yeah.
quite interesting is the fact that RS is very large.
That's right. That's right. That's right.
So there's something wrong in your considerations here.
So basically, the bottom line is that we don't need to assume the interaction is smaller than the gap. For fractional chain oscillator, even if interaction is larger than the gap, it can still be the ground state. We have models demonstrating that. And for TMD, for release TMD, the story is actually slightly more complicated. If I really do the first principle calculation, the TMD material, it has actually 3 chain number plus 1. Next one is -3, which means it's kind of like lambda. So the first 3 band chain number, next one is chain number -3. Okay, well, we can talk about these details afterwards. But anyway, this this bandwidth is too large and low mobility and non-chiral limit was actually the main reason that people believe this will not work. Back in 2021. Okay, but we look at these 3 problems more carefully, and we decided actually, these 3 problems can be addressed. Okay, so first of all, this bandwidth problem. So the bandwidth is too large, band gap is too tiny. Okay, so this problem, it turns out we find a very easy solution for this. Okay, because from previous study about fractional chain bands, we know what we need is band gap delta to be large, bandwidth W to be small, which means we want this ratio of band gap to bandwidth to be large as possible. Once we know our target, then it's just optimization. We have our tuning parameter, which is the twisting angle. We just scan the twisting angle and see which twisting angle gives us the largest gap to bandwidth ratio. And by just doing so, we find that about 1.4 degrees for MOTE2, this band gap to width ratio can be more than 10. That's based on our previous experience. This is actually good enough. And this is band structure. And you can see the top band, by changing the theta angle, twisting angle, the top band can be really, really flat. The bandwidth is much smaller than the gap. Okay. And the second problem, we don't have chiral limits. There's no ideal quantum geometry. We look at these concerns and decided this is actually not a real concern. This is because in previous studies, over the last 1 decade or so, we actually tried numerous models for this fractional chain with this state. And most of those models don't have ideal quantum geometry. Ideal quantum geometry makes the gap larger, but the models without quantum geometry can also stabilize this state. Okay, so we need to try it, really dump it into numerical simulation and see what will happen. Finally, the problem low mobility. This is something we can't do anything with it because there's no reliable theoretical tool to address the impact on low mobility. So we just hope that someday the mobility will be high enough and we're not ruining our fractional states. Okay, so and this is what we did. We look at the MOTE2, this is material we chose, and we twist by layer. And we use the first principle parameters, which is already widely available at that time. We use the first principle parameters to calculate the Marie flat band structure and wave functions. And I want to emphasize here is there's no free parameter. We copied the first principle parameters from published work. We didn't do any modification to the model. And then once we have this Marie flat band, we dump this Marie flat band into a computer, and that computer finds the exact ground state and find the exact energy spectrum and see what this state is. Okay, that's what we did. Okay, so we chose the twisting angle to be roughly about 1.3 or 1.4 degree. So on this twisting angle, we have two flat bands. One in the K value, another flat band in the K prime at opposite K. Okay, and for K value, the flat band has particles with spin up, and the Chen number is +1. For the K prime value, the flat band has opposite spin down, and opposite Chen number is -1. Oh, I should mention that this is actually whole bands. So this is actually the valence band. So we should dope whole. This is whole dope. Okay. And the reason these two values have opposite spin and opposite Chen number is because of the time reversal symmetry. Time reversal symmetry connect these two values, so they must have opposite Chen number and opposite spin. Okay. Go ahead.
So first of all, these are the bands that you keep, right?
That's right. That's right. That's right. We didn't keep the remote bands.
And then you mentioned about that these are not ideal bands, but so how evenly is the Berry curvature distributed? Is it
Not very even. Not very even at all. Not very even at all. It's quite not even. This is actually, we know, that's not a big problem because in the earlier, lattice model we studied, most of them, the Berry curvature is actually very, very uneven.
Why do other people then discuss this ideal?
Well, if the Berry curvature is actually very even and the ideal quantum geometry is achieved, one can show that the gap is larger. So I will show another study slightly later. When you go towards this ideal limit, the gap becomes larger and larger. It makes things better, but it's never an essential ingredient. But of course, we know if we are too far away from this ideal limit, eventually CW will win. So it's a matter of numbers. So we need to do the calculation to really know the answer. And there's no just one sentence principle one can find the answer. Okay, great. So this is the setup. And we put, before I discuss our simulation, let me briefly discuss what happens at integer field. If we are at the integer field, we fill on both bands. And then this is a quantum spin Hao insulator. We have spin up with Chen number +1, spin down with Chen number -1. If we fill so we fill only one of the bands and leave the other band empty, then we get a spin fully polarized ferromagnets. And this ferromagnets happens to be a integer quantum non-Hao state. Because if we have if particles fill one of the band, we have a non-zero Chen number. Okay. But what we are looking here is not at integer filling. We are looking at the fractional filling, and we put some fractional filling here. And in our simulation, I think we consider a couple, 1/3, for example. And then we put strong repulsive interactions between these particles and the C. Go ahead.
Sorry, just a simple question.
Yes.
So you're thinking of molybdenum bitelluride as somewhat similar to graphene. So one of the carbon atoms is like molybdenum, and
That's right. Yes.
Tellurium
Yes.
are the other carbon
That's
atoms.
right. It is actually slightly more complicated because it actually it has 1 MO 2 TE, and the 2 TE is actually auto plane. So slightly more complicated, but it's roughly
Yeah,
that's right.
looking down from the top.
That's right. That's right. Yes. Yes. Yeah. You're right. And it breaks the 6-fold rotation symmetry.
Right.
So the DR point becomes massive.
But obviously they're totally different in reality. So does that not cause any issues with this?
Oh, they are totally different. And the reason we have flat band here is also quite different. For example, twist bilayer graphene, we know at least when we go to the chiral limit, we know it's exact flat band, blah, blah, blah. Here it happens to be flat. We don't have a real reason to prove, this must be flat. So, and in fact that, this was some earlier, I will mention this slightly later. We use some earlier first principle parameters, and the recent first principle study indicate that it's not actually a magic flat band here. It's actually a window of angle. The band are totally flat, which is actually a good thing for this fractional state, which means that you don't need to tune to a particular angle. You just roughly around that angle, you always get the same state. Okay, so it's actually, it's actually very different. Just happens it has a flat band. And the flat band numbers is actually totally different. And Ali mentioned the for graphene, it's 8 flat bands. Here it's just 2. It's much simpler model than graphene. Okay, so let's look at the fractional filling and the repulsive interaction. What's going to happen? The first thing we observed in the numerical simulation is ferromagnetic order. It's ferromagnetic order. And this ferromagnetic order is actually very, it's not unexpected at all. It's just Stoner ferromagnetism. It's because we have flat band has a large density of state, so Stoner criteria can be easily satisfied, even if we just have a little bit of interaction. And because Stoner criteria is satisfied, we have ferromagnetic transition. Ferromagnetic order break the time reversal symmetry. It means that it will push up one of the spin band and push down the energy of the other spin band. Okay? So the 2 spin band now will lift their degeneracy into the same energy. If they were on the 1/3 or 2/3 filling, it means that all the particles will go to the low energy band. In other words, we get a ferromagnetic state with full spin polarization. This is a little bit different from a regular, non-flat band Stoner ferromagnets. For non-flat band, Stoner ferromagnets is partially spin polarized. But for flat band, it's fully polarized. All the particles go to one band. But all the particles to one band, but we are in fractional filling. The particle is still not enough to fill this band. Okay? The particle cannot fill this band naively where it expects Fermi liquid, but in the flat band system, that's not the case. We find actually the insulating bonds and fractional filling. And we carefully check this insulating ground state, and we find that it's not a charge density wave. There are no CW order. And we also calculated the topological index, the Chen number, which is also the Hawk connectivity, the same thing. And we find that the Chen number of Hawk connectivity is fractional. So this is the insulator with no CW and fractional filling, no CW order, and has a fractional Hawk connectivity. So that by definition is a fractional fractional chain state. And of course, in addition, we checked all other tools that we could use to probe the fractional topological state. For example, the quantum entanglement entropy, etc. And they all indicate this is indeed the fractional state. Okay. So here is a phase diagram we found. Horizontal axis is twisting angle, vertical axis is interaction strength, and we can see that a very large region of the phase space, this fractional state is a ground state.
Sorry, for which filling is that?
Oh, this is actually 1/3 filling.
Because in experiment,
Externally, they find 2/3.
they typically start from above, right? They start from,
That's right.
that
That's
is
right.
higher than a half.
That's right. Yes. So experimentally, one didn't see 1/3 fractional state. One see it and 2/3 and 3/5. Yeah, but the simulation we did is 1/3. Okay. So I want to emphasize that in our simulation, there are no free parameter. All the numbers comes from first principle. We can't adjust anything. And we can't make any approximation in this model. And still, this fractional state appears as a natural state, obviously. Okay? So, as I mentioned, in the last 10 plus years, we have been studying this fractional state in numerous models. But in almost all the models I tried before, we need to tweak the model somehow. We need to do fine tuning to the model to get this state. But somehow for this traditional dichotomy, it works like magic, right? Nature just puts everything properly for us. We don't need to do anything, and we get this state. And independently, roughly the same time, Liang Fu's group looked at another transition to dichotomy here, WT2, and they find the same conclusion. Okay, so on the theory side, we have full confidence about our theory, but we try to compare theory with reality. There are always some complications and potential problems. Here, at least, we have 3 potential problems. First of all, we use first principle parameter, so it's no free parameter, adjustable parameter in our model. But the first principle calculation, we know that it's not always reliable. Whether the parameter we use is right or not, that's actually an open question. Okay. And secondly, same as all theoretical models, we can't include all the phenomena in this theory, in this model. So some of the phenomena we ignored when set up this model was that those things ruin our fractional state. We can't answer. And finally, this problem of low mobility, and this low mobility ruins this fractional state. Of course, we have no answer again. And we eventually decided that there is nothing we can do here. Okay, these 3 questions can only be answered experimentally, and theoretically there is no way to address these 3 questions. And luckily, we didn't need to wait for long. Okay, just 2 years after our study, the Sheldon Schiff's group from University of Washington and Kim Matt and Jichan's group from Cornell, they look at the same material with MOT to exactly the same material, okay? And they found this fractional states. Of course, we didn't get everything right. For example, the filling, we did 1/3, and they found it's 2/3 and 3/5. And more importantly, the twisting angle, we predict about 1.4 degree. They find this fractional state about 3 or 4 degree, 2 or 3 degree twisting. Okay? And eventually we figure out, eventually actually first principle people figure out the reason. It's because back in 2021, the first principle calculations there didn't consider lattice distortion induced by this new restructure. And recently in the new, latest numerical, band structure calculation, including the effect contribution from lattice reconstruction, one can prove that indeed the 3 or 4 degree give us these 2/3 so 3/5 fractional states. And shortly, so the first experimental signature comes from optics measurements. And shortly after, Sheldon's group and another group, Professor Li's group from Shanghai Jiaotong University, and they showed that in transport, fractional Hawk connectivity measured in the same setup. And slightly afterwards, Longju's group found that we don't need actual transition metal dichroic lines. If one use pentalayer graphene on HBN substrates, one can also get fractional chain oscillator and 0 magnetic field. So now we have at least 2 different experimental systems give us this fractional state and 0. Okay, so we have this fractional field, fractional states. We can realize it with Landau level and magnetic field, which is called the fractional quantum Hall effect. We can also realize the same effect without magnetic field, which is called the fractional quantum anomalous Hall effect. So the natural question to ask is whether these 2 states are the same state or they are totally different. Okay, and the answer depends on whether we're talking about the ground state or we're talking about excitations. Let me show you the answer first. If we're talking about the ground state, then indeed these 2 states belong to the same quantum phase, and they have exactly the same topology, and they belong to the same quantum phase, and they can be adiabatically tuned from one to each other without going through any phase transition. But if you look at excitations or thermal excitation, story is a little bit more complicated. For excitations, the 2 states are similar, but also have some important differences. Okay? So let's first look at the ground state. So ground state, fractional quantum Hall and fractional quantum anomalous Hall are exactly the same quantum states, and they have exactly the same topology. The reason we know that was from this study we did with Ginandra Jain's group about actually more than 10 years ago, back in 2012. Okay? So back in 2012, we look at this Hamiltonian. This Hamiltonian is composed of 2 Hamiltonians. We have a Hamiltonian of fractional quantum Hall state, HFQH. So this Hamiltonian is described as a fractional Hall state. And this Hamiltonian describes a fractional quantum anomalous Hall state. Okay? And we add these 2 Hamiltonian together using a control parameter x. X is a real number, its value is between 0 and 1. The reason we want to do that is because in this setup, we can use x as my tuning parameter. If x is 0, first term is gone, we have the fractional quantum anomalous Hall effect. If x is 1, second term is gone, we only have fractional quantum Hall. So this Hamiltonian actually offers us a tuning parameter x that can smoothly move a fractional quantum Hall Hamiltonian into, fractional quantum anomalous Hall Hamiltonian into a fractional quantum Hall Hamiltonian on backwards.
I have a question.
Yes.
Does your FQAH generate the whole sequence?
FQAH, actually, it depends on model. Actually, usually it doesn't. Usually it doesn't.
Right, so I'm not quite sure I know what you mean by this interpolation scheme. Because you have fractional quantum Hall effect,
That's right.
you have the whole sequence.
That's right. Yes.
Over here, we don't have the whole sequence.
That's right. That's right.
Then how are you gonna interpolate?
So typically, fractional quantum Hall has more states than fractional anomalous.
Right.
So we choose a fractional quantum anomalous Hall state, and then find the corresponding fractional quantum Hall state and do this construction. So if I do 1/3 here, we're doing 1/3 here. We choose the same filling and same corresponding state. We don't change the filling. If we change the filling, of course, it cannot be adiabatically connected anymore. But we know this.
So your statement then is the 1/3 state the same in both cases?
That's right. That's right. Of course, they need to be same filling, same topological state, same Hawk connectivity. Different Hawk connectivity, of course, they will be different states.
Okay, so what other states do you get besides 1/3?
Say actually no, depends on model. 2/3, 3/3, 3/5, etc.
You can actually get 3/5.
Yes, not in this model, but in other models. Sorry, not in the model I mentioned to you earlier on, based on the wrong first principle calculation. But in the latest, if one use the latest updated first principle parameter, then in the MOT2 model, one could get 2/3 and 3/5, exactly the same as external
But
observation.
those models will also give you 1/3.
No, this model do not give 1/3. That's actually. Oh, of course, we can doubt it because it's a post-station. It's the experiment first have this result, then people redo the first principal parameter, that's the first calculation and dump it into exact solution, exact dimension. But with this new parameter, in the exact dimension of MOT2 model, indeed they see 1/3. Sorry, they see 2/3 and 3/5. They don't see 1/3.
Okay, so with the updated parameter,
That's right.
do you get that 1/3 is a Wigner crystal?
1/3, I don't remember. It's not a fractional quantum. I don't remember it's a gapless state or Wigner
So
crystal.
the
I don't,
experiments seem to be telling us it's a Wigner crystal.
sorry,
Is that what you're getting?
not in my model. My model was using the old parameter. And sorry, for the
Now I have new knowledge. If
For
you
the
were-
new knowledge, I don't remember, because I didn't do the new principle, I didn't do the first principle calculation, I don't know. And there are multiple groups doing first principle calculations, and they have different parameter. Each claim their parameter actually, perfectly fits the experiments, but I didn't check which one fits better, which one fits worse, okay? So honest answer is I don't know. And experimentally, I believe 2/3 is fractional Hall, they see it. 1/3, I believe what experimentally see is actually a metal. It's the electron 1/3 is signal. Whole 1/3 is metal. That's my memory about the experiments.
No, sounds good.
Yes, go ahead.
So FQAH
Yes,
comes from a lattice, and I guess
That's right.
FQH comes from a continuum system.
actually,
Right.
Yes.
The other one is continuum.
That's a great question. So in this particular study, what we did is extremely dense Hofstadter lattice.
Extremely dense one.
Hofstadter lattice.
Uh-huh.
So Hofstadter lattice is not literally Landau
I
level,
see.
but when it's very dense, magnetic flux is tiny. It's very close to Landau level. So that's what we did. This side is Hofstadter with very dense lattice. This side is a discrete lattice model.
Because I thought there were arguments that sort of the FQAH
Uh-huh.
has additional symmetry used in something. No,
Additional semi.
because of the.
Um,
Okay, no, forget about it. Okay. get the question.
right, yes. Yeah. Okay, so basically this is setup we tried. And from the numerical simulation, at least for several models we tried, when we tune this value of x, the gap never close from x equals 0 to x equals 0. Gap don't close means when we go from x equals 0 to 1, there's no quantum phase transition, and there's no topological phase transition. And these two states belongs to the same quantum phase. It's just two corners of the same quantum phase, and there's no phase transition between them. Because there's no phase transition between them, we know for sure all topological indices will be exactly the same in these two cases. Yes.
We know from the Cornell that in fact, the gap doesn't, the single particle gap doesn't have to close. But you can have different.
This is many body gap. This is from exact addition. We're looking at many body gap. Not the charge. Not charge. The excitation gap, the gap between ground states and the excited states, that gap don't close. That means there's no quantum phase transition. There's no level cross of any type. Okay, we can discuss that, but there are no level crossing. That's fine. Yeah. Okay. Okay. Then for Fletcher bands, in addition to another difference between Chen bands and the Landau levels is Fletcher bands can have higher Chen numbers. And in another study a few years afterwards, we showed that the higher Chen number fractional quantum higher Chen number bands fractional quantum non-Hall band states is also adiabatic connected to fractional quantum Hall states. But there we need to use fractional quantum Hall multilayers to connect with higher Chen number bands. Okay, nevertheless, for ground states, we know they are adiabatic connected, and one don't need to close any gap to go from one to another. So for excitation, the story is a little bit more complicated. So before I discuss about detailed physics about excitations, I need to introduce one theoretical tool, which is so-called composite fermion language, composite fermion description for fractional Hall effect. So a composite fermion is basically a composite object. It's made of one electron plus 2n, 2 times integer, magnetic flux quantum. And nice thing about this composite fermion description is that in Landau levels, if we look at electrons are very strongly correlated. But if we map electrons into this composite fermion, composite particles, and look at these composite fermions are nearly free particles. They nearly have no interaction with each other. So this Landau level fractional quantum Hall system, although it sounds like a very exotic, topological fractional, non-abelian state, fractional topological state, but in reality, it's essentially just non-interacting physics. We can map everything to composite fermion, and using the non-interacting picture of composite fermion to get pretty much everything for Landau. Okay. So because these composite fermions are fermions, they have very weak interactions with each other. Then we know that there are only a few possible states these composite fermions could give us. Okay, weakly coupled fermions can give us Fermi liquid. If this composite fermion form a Fermi liquid, then the corresponding state, if we map back to the original electron, we get the so-called composite Fermi liquid state. And the 1/2 field lambda level is believed to be described by this picture. And composite fermion, very weakly coupled composite fermion can also form a band insulator. If composite fermion form band insulator, when we map it back to the original electron, we find abelian fraction quantum states, like for example, Laughlin state or Jane states, etc. And weakly coupled fermions can also form Cooper pairs, superpairs. If this composite fermion forms Cooper pairs and forms a superconducting state, when we map it back, we get a non-abelian grid state with Majorana fermion excitation, etc. Okay, so bottom line, lambda level are described by very weakly coupled composite fermions. So for fractional quantum non-Hall effect in fraction bands, one can have pretty much the same description because it's adiabatically connected to fractional quantum Hall states. But with one caveat. That caveat is that this time for the fraction bands, even if we map it to composite fermions, these composite fermions still have very strong interactions with each other. Lambda level is very special. In lambda level, if we do this mapping, the composite fermion is nearly free. But for the fraction bands, this composite fermion has very strong interactions with each other. Yes.
To get composite fermions, you need a singular gauge transformation.
Yeah, with a flux, yes.
What's the singular gauge transformation when you don't have a magnetic field?
Well, one can always put a flux there.
What does it mean? I mean, there's no magnetic field.
Well, sorry, what's that?
Statistical flux.
That's right. That's right. That's right.
Who cares? It's just good.
That's right.
In the composite fermion picture, delta B is 2 minus alpha. Okay, so what is being attached?
Well, the story is long. I think we should probably discuss this afterwards.
Use the variant field because it's K-dependent.
But roughly speaking, the picture is like this. The 2 pi flux and the 0 flux is actually not fundamentally different. When we say fractional non-Hall state has no magnetic flux, it's actually we can do a gauge transformation to transfer it equivalently to each unit cell has a 2 pi flux. That's the same state, just a gauge transformation. It needs to use a single gauge transformation, but these two states are dialectic connected. Everything works there would work here.
Well, I guess that's what I'm trying to understand.
Yes. And if yeah, so in most
I understand is how the argument works in the
Right.
field.
Right.
I do not understand how the argument.
I agree with you in the description of composite fermion for this fraction band stuff. Typically, people take the continuum limit, ignore the lattice, and argue things work the same way as lambda level. A rigorous demonstration usually is not done for the lattice model to do the flux attachment. But for lattice model, there is one model we know how to, actually two models we know how to do flux attachment exactly. That's a square lattice and Kagami lattice. Actually, this was originally proposed by Eduardo. Eduardo is an expert on this. For square lattice and for Kagami lattice, one can actually write down a discrete Chern-Simons scale theory, which gives you a flux. And there we know for sure what's going to happen.
Yeah.
But not for most flat band case people discuss in literature.
That has nothing to do with this.
Uh-huh.
I mean, he's at the office very nice to me, so no, this has nothing to do with this.
Okay, let's discuss this afterwards. Okay, so the bottom line here is that even if we do any mapping we want, the particles here are strongly correlated in flat bands. Okay, and this so basically this is the physics picture. If we are looking at the ground state physics, fractional non-Hall and fractional Hall are the same phase. There are no quantum phase condition between them. But if you look at excitations, then there is a crossover between these two phases. And this crossover is between the case where composite fermions have strong interactions with each other and composite fermions with nearly no interactions with each other. Okay, and this has important consequences. Okay, so let's look at a fractional quantum Hall state or fractional quantum non-Hall state. And let's start from the lambda level side. In lambda level side, composite fermions are basically a band insulator. Okay, if we have band insulator, we have valence band, we have a matching band for composite fermions, and there's a band gap. Because composite fermions are nearly free in lambda level systems, we have free fermions on the band insulator. If we have free fermion band insulator, there's only one gap, that's a band gap. no matter we measure the gap for charge excitation, or no matter we measure the gap for charge neutral excitation, we are always measuring this band gap. Everything is controlled by the band gap. So whatever excitations we measure, we always find the band gap. Okay, but that would not be true for interacting composite. For interacting composite fermions, the charge excitation, the energy cost to add and remove a particle, is still controlled by the band gap. Okay, but charge neutral excitation is not controlled by the band gap. This is because the charge neutral excitation for interacting fermions is a bound state of particle. Okay, if you have particle hole bound state, stronger interaction means stronger bonding energy. Stronger bonding energy means this energy cost to create this particle hole bound state is lowered. And from our numerical calculation, our numerical simulation, this particle and hole bound state actually is extremely low energy. And the gap for charge neutral excitation is much smaller than the gap for charge excitation. Then they differ by at least 1 order magnitude for the models we study. Okay, so this energy scale separation is a direct consequence of strong interactions between composite fermions. In lambda levels, this will never happen. It's the same gap. But for fraction bands, if we measure the charge excitation and charge neutral excitation, we will have very different gap. Charge excitation has much larger gap. Okay, and this has the direct experimental consequence because we can measure charge gap in experiments. We can measure charge gap through, like, say, longitudinal conductivity, fit it to the activation behavior, or we can measure the density of state using STM or point contact. Density state will directly give us the gap. Okay, this gives us the charge gap. For charge neutral gap, we can measure it experimentally through thermal excitations. For example, we measure heat capacity or heat conductivity, that matter, and fit the result to the activation, thermal activation behavior. And this gap will be the charge neutral excitation. And we can also measure for quantum Hall, we can also measure the on-site temperature of quantum Hall plateau. That's the temperature where the plateau started from. We call it T star. This T star would also be comparable with charge neutral gap. Okay, and we measured the density of state numerically, and we measured heat capacity and T star numerically, and compare them, and find that the charge neutral gap is actually dramatically smaller than charge gap. They differ by at least 1 order magnitude. Okay, so on the experimental side, for MOTE2, T star is measured, on-site temperature of the quantum Hall plateau, and also the charge gap from thermal activation behavior of longitudinal transport is also measured, and they differ by about 1 order magnitude. Qualitatively agree with the theory picture I described here. Okay, and here is some technical details about how did we measure those quantities. Because we measure the temperature dependence, we can't use the traditional like excitation or DMRG techniques, which handles zero temperature physics. What we use is the latest, is a new algorithm known as exponential tensor renormalization group. It's basically finite temperature version of DMRG. It is numerically exact and can calculate all kinds of measurables and physical observables and finite temperature. Okay, so basically the strong interaction between composite fermions on the non-Hall state tells us that in the flexion bands, we should expect very low energy charge neutral excitations. But what are these charge neutral excitations? This charge neutral excitation is actually not exciton. It's actually what people call the magnetic roton. Okay, so to understand what is magnetic roton, let's look at first the Fidel oscillation. Let's first look at the metal. Okay, so in a metal, we know that if we put an impurity in a metal and look at electron density near the impurity, we will see this oscillation of electron density, this oscillation in real space. And the wave vector of this oscillation is roughly 2kF. It's twice the Fermi wave vector. If we put an impurity in an insulator, no Fidel oscillation should be observed because insulator has no kF. So there should be no Fidel oscillation. But not for a fractional quantum Hall insulator. Okay, I believe this was a reference Ali mentioned this morning. So in 1985, 2 groups published this 2 back-to-back work almost simultaneously, and they both look at the fractional quantum Hall state. Fractional Hall state we know is an incompressed state; it's an insulator. But if we put a charge impurity and look at the electron density near the charge impurity, we see these oscillations, just like Fidel oscillation. It has no Fermi surface, but it has this Fidel oscillation. This Fidel-like oscillation, of course, does not come from Fermi surface because we know for sure fractional Hall state has no Fermi surface. And the origin of them is this charge neutral excitations I was describing earlier. Oh, and for fractional quantum anomalous flexion bands, this type of Fidel-like oscillation is also observed in our recent numerical studies. And we look at the fraction bands, and the integer filling, we see no oscillation. And the fractional filling for the fractional state, we see high, low density. We see oscillation. And the origin of this oscillation, as I mentioned earlier on, is because charge neutral excitation. So this dashed line here is a cartoon picture of the charge neutral excitation dispersion condition. As we can see for integer filling, the energy minimum is at typically is around 0 Q. So this integer filling excitation is typically accidental. The energy minimum is at 0 momentum. But if you look at the fractional state, the energy minimum is typically not at 0 momentum, but at some finite momentum. Because the energy minimum is at some finite momentum in the fractional quantum Hall literature, this excitation is referred to as a Roton or magnetic Roton excitation, to emphasize the fact that it carries finite wave vector. And this finite wave vector is the reason why there is a density oscillation near impurity. It's because we have low energy fluctuations or low energy excitation that carry finite momentum. Okay, so that is about the Roton excitation. So let me do a quick summary. So in Flattron bands, one key difference between Flattron bands and Landau levels is that the composite fermion has very strong interactions. This means that the on-site temperature of the fractional or plateau will be much smaller than the charge gap under the scale. And we should see, Fidel-like oscillations near impurity. Okay. Okay, so we know that the Flattron bands have very low energy and very soft Roton excitations. Can we go even further? Can we even enhance the interaction between composite fermion even further to make this gap even smaller, to make this mode even softer, and maybe even make the gap negative? Okay, it turns out indeed we could do that. In recent studies, we find a set of models where this gap softening indeed takes place, and we can tune some control parameter, typically it's interaction strength, to tune the gap size from positive all the way to negative. Okay, and when the gap is positive, as we reduce the gap size, what we observe and what we should observe is a diverging CDW charge density wave stability. This is because Roton excitation carry finite momentum, so it's directly coupled with CDW. When Roton becomes softer and softer, charge density wave fluctuation becomes larger and larger, and stability diverge and function 1 over the gap. Okay? And when the gap becomes 0, CW stability really diverge. It means this is quantum critical point. If we go beyond the quantum critical point, this Roton actually has negative energy. For boson with negative energy, it means that we will see BEC, or see condensate. And this condensate of Roton basically means that the system developed the CW charge density wave point.
Okay. CDW and Wigner-Gris was the same in this context?
Depending on who you talk with. Some people will say this is definitely not Wigner-Gris, so this is CW, because we have a lattice. In the sense that this is not freely adjustable. So that's actually another key difference between Rotons in Landau levels and Rotons in fractional trend bands. In Landau levels, this is because this energy minimum is determined by filling, and you can tune it by filling. But in Flattron bands, it's not. In Flattron bands, this energy minimum typically pinned by the lattice. It's on the lattice high symmetry point, independent of the filling, typically. Not always, but typically. Okay, so with in the presence of lattice, Wigner-Gris is not a well-defined concept. Okay, anyway, so bottom line, if we make the interaction between composite fermion stronger, we will see we could Roton condensate induce the second order quantum phase transition to a CW order state. I want to emphasize that this second order phase transition to a CW state is impossible for Landau levels. This is because Landau levels are isotropic. For isotropic system, CW or Wigner-Gris transition can never be second order, it's always first order. And for Flattron bands, because of lattice break the rotational symmetry, then the second order phase transition becomes possible. Okay. Another thing I want to highlight is this CDW state induced by Roton condensate is also non-trivial. This CW state has only two possible scenarios. First scenario, this CW state is a metal. This Roton condensate gives us a CW, but CW is not the insulator, but the metal. It's a conducting CW. The second scenario is that the CW after Roton condensate is the insulator, but if it's an insulator, it can't be a trivial insulator. It must be a fraction quantum non-tau insulator. So this CW state induced by Roton condensate through a second order phase transition can have only two options: either CW metal or fraction quantum Hall CW. It can't be a CW trivial insulator. Okay, and this is, I want to emphasize, this is not hand-waving argument. We have actually two different numerical models. Each one realized one of this scenario, and it's backed by rigorous models and rigorous numerical simulations. Okay, so let me skip this summary. So I have about 10 minutes or some.
Well, we're sort of now you're speaking for 1 hour.
Okay.
I know I interrupted you a lot.
Okay, so then I will skip the last part and just mention one quick conclusion. So in the last part, I demonstrated that to get this flat term bands and the fractional chain oscillator, one don't necessarily need bilayers. One can achieve this by using just a single layer 2D material with the quadratic band touching. Quadratic band touching basically means the dispersion is quadratic near the band touching. So if you use such a material with just a single layer, then apply a periodic strain. Then this periodic strain will give us the horizontal axis here is periodic strain. It will give us 0 bandwidth, 0 bandwidth, 0 bandwidth. And this flat band also has ideal quantum, can also go to chiral limit, can also have ideal quantum geometry, and the Berry curvature distribution for the second magical band here is 1 order of magnitude more flatter than twist bilayer graphene. So presumably it will give us fractional state with even larger gap. Okay, so I will skip this part and I will conclude with my last slides. Where is my last slide? Okay, yeah, I will conclude with this. This is my last slide. Okay, so for my last slides, I will make some irresponsible speculation about what's going to happen next. Okay, so we know that these fractional states need 2 ingredients to realize. One is topological band. Another is this band need to be flat. It's flatness. Okay, these 2 ingredients, if you look at it, it's actually remind me a lot about heavy fermion compounds. Okay. We know in heavy fermion compounds, all heavy fermion compounds have flatness. And we know some of them can be topological, like what the Pierce and I showed more than 10 years ago. Okay? So it seems to me that a natural question we can ask here is that whether it's possible to use heavy fermion compounds to get this fractional states. And heavy fermion compounds has one key advantage. It's really a strongly coded system. It's not just like twist bilayer graphene. Twist bilayer graphene itself, the interaction is not strong. We make the interaction strong by making the energy scale down and makes the interaction look strong. But if we can get the same effect from heavy fermion compound, interaction is already strong. So all the energy scale should be proportionally get larger. Hopefully we can get some fractional state with even higher gap and higher and can function higher temperature. Okay. Now theoretically the answer to this question should be yes, because heavy fermion compound has the right ingredients. But of course the real question and that's the real valuable question is when and where we can find a heavy fermion compound that properly combines these 2 ingredients together and give this fractional states. Okay, I think this is a good point to stop, and thank you for your attention.
Can I clarify your scenario about the many body gap? Are you saying many body gap closed?
Maybe don't close, no gap close.
So if you did have a topological transition,
At least some gap should close. Here, no gap close.
so the standard picture is that it's the charge gap if the system is not interacting.
Non-interacting, there's only one gap. Charge gap and every gap without one gap, not gap close.
In the presence of interaction.
Right.
What the charge gap is doing is relevant.
That's right. It's a many body gap.
Yes, many body.
That's right. That's what we find to be not closing here,
Yeah.
not the charge gap. Yeah.
Okay, so we wrote the paper.
Yes. Yeah. I know your work. It's a beautiful work. I totally agree. So we are not making that mistake. We are not looking at the charge gap. We are looking at the true gap. We should close the transition, but it doesn't. Yeah, and actually this is related with the separation of gap scales. And I mentioned that the charge gap is huge in this system, but the charge neutral gap can be very, very tiny. We were looking at the right gap. I'm pretty confident about that.
Very naive question. I mean, the Roton thing went by quite quickly, but if I just have a classical liquid and I have an impurity, it'll have an oscillating density around it. I don't need a Fermi surface. Any classical liquid.
That's right. Yes. So yeah. So basically, any system with density correlation function with some structure in K space will have this oscillation. That's totally true. I totally agree. I totally agree. So in that sense, Roton is not, for Landau levels, one can show that indeed this Roton excitation is this, one can calculate everything exactly. Indeed, there is a finite minimum, a finite momentum energy minimum, and it is called the Roton. But that is actually nothing like as fundamental as topology. It's not some really universal feature.
It's because you've got dense liquid.
That's right. That's right. Yes. Exactly. Yeah.
Thank you very much for the talk. I just wanted to make a small comment. So you talked about your work on this, square lattice or Agomel lattice where the theory is thought about maybe you can see fractional quantum Hall effect without any external field. So we recently published a work in actually Agomel ferromagnets, and we think that we see fractional excitation charge. But of course, you cannot see it through transfer because the band structure is just super complicated, but at least at some bands, we think that there's fractionalization. We see spectroscopy.
I see. So is this work already posted or published?
It's already published in
Oh.
Nature.
Oh, great. Yeah, so sorry for my ignorance. I didn't know that. Yeah, I'll be very happy to read it. Yeah, thank you.
Just was curious about a comment you made at the beginning
Uh-huh.
when you said lattice model with chiral symmetry, a flat band with chiral symmetry is most similar to a Landau level. Because naively from the topological periodic table of topological insulators, if you've got chiral symmetry, you'd be in class A3, not A.
That's right,
which has
yes.
no zero Chern number.
That's right.
So it just seems a little contradictory.
That's right. So the full story about the chiral limit of twist bilayer graphene is it has actually 8 bands, as Ali mentioned earlier this morning, and it forms pairs of Chern number +1, Chern number -1. The nice thing about the chiral limit is that we can choose a basis to separate these 2 bands.
Okay.
And if we separate them, one has Chern number +1, one has Chern number -1, and the +1 Chern number band is exactly the same as the Landau level, or sorry, almost the same as the Landau level with the Chern number +1. The other one with -1. There is always a degeneracy.
Okay.
So that is actually a key point for fractional quantum non-Hall effect. It always involves a spontaneous symmetry breaking of time reversal symmetry. We need to split this. It's need a ferromagnetic transition, basically.
Okay.
Yeah. So I didn't go into detail. You are totally right. It has 2 degenerate bands.
Yeah.
But one can separate them. If I separate them, each one of them has the same kind of wave function, like Landau level. Yeah.
Excellent talk. Okay, I'm slightly confused about the bits where you can tune X from the anomalous quantum Hall to the just fractional quantum.
Yes.
So I get the argument, kind of, but couldn't you just take any spontaneously symmetry broken state and apply an external field that breaks the same symmetry the same way, and then tune your interactions and argue the same thing? Couldn't I take a ferromagnet, apply a B field in the same direction as the spins, and then increase temperature until it should be a paramagnet? Say, look, it's the same thing, and I can close a gap, so it's the same state, but it's not the same state. Similarly, you're going from an anomalous state to applying a B field and then getting a fractional whole state. Saying they're the same because they're graphing.
This is actually a good point. So fractional quantum non-Hall state, by definition, is actually not the same as fractional quantum Hall. In the sense, fractional quantum non-Hall need a spontaneous time reverse symmetry breaking. One need the ferromagnetic transition. So what we demonstrated there is we ignored the symmetry difference. We're just looking at one symmetry breaking state. Compare it with a fractional Hall state with magnetic field up. There is another degenerate state that is connected with magnetic field down. We are not arguing that it's exactly the same state in the sense that one is external field breaking time reversal, the other is spontaneous. We didn't touch that level. We're showing that if one has the state can be affected deformed to the other. Which means that they have the same topology, which means the state have the same topology. But symmetry breaking, definitely you are right. One can actually add additional ingredient to distinguish them. But under naive topological level, they are the same.
Okay.
Thank you for a beautiful talk. I really have 2 questions. Let me focus on the last spec. Irresponsible speculation.
I'm not responsible for that.
What would be the requirements for that hypothetical material? First, would it have to be 2-dimensional?
For 3D, there are theory expectations, there are theory proposals. But for 2D, it's a system we really know. If we have flat band interaction, this will definitely happen. In 3D, it's kind of like various spin liquid states. We don't really know for sure what this one state is. But in 2D, we have better confidence.
And it would be an insulator?
That's right. Yes. Oh, sorry. the band itself should be a separate band, away from the other band, which is flat and topological. But we are doing fractional filling.
So we need to start out with a very flat.
Very flat,
band,
topological band.
and it has to be unhybridized,
It need to be topological.
right, so.
Topological in the sense that it need to involve the band volume already.
Right,
Yes,
so it needs to be separate from other bands.
that's right, need to be separate from other bands. Or other bands don't do some, it need to be separate from some other band by itself, or bounded by simultaneous symmetry. For example, in traditional dichotomy, we have two, one is number one, it's number minus one, they're totally examined. It's interaction have to push one away and then keep this one.
Very good.
So eventually we need one band with a well-defined chain number, non-zero chain number, and fraction phase. The other band and the non-entangled, whether it's nearby or far away, is not important. The important thing is after return on inflection, other band is different.
And on the earlier part of the talk, you've made extensive use of sine-free Monte Carlo,
That's
which is a great tool. My question was, in your model, when you had the attractive interaction with the pseudo gap, do you know of any approximate approach that enables you to reproduce those kinds of results?
You mean
Any
numerically?
approximate, no,
Numerically or analytically?
no, analytically.
Analytically, actually.
Roton method or whatever.
Right. Analytically, actually, we know the answer. Analytically, let me go back to the slides. Analytically, the exact solution exists for zero temperature, although it does not directly exist for finite temperature, but we can use zero temperature information to interpret it.
Yeah.
Analytically, we can prove that if this band is totally flat, with no dispersion at all, then this Hamiltonian has an emergent SU2 symmetry. The SU2 symmetry is pairing order parameter, conjugate of pairing order parameter, and the density. These three operators is like a spin rising, spin lowering, and SZ. They commute with Hamiltonian, and they form SU2 symmetry.
And you would get a nice sharp gap function in that case.
Right? There we can, because of SU2 symmetry, superconducting finite temperature must be zero temperature.
Yes.
We can't get any finite temperature superconducting transition. And it's a bandwidth break this symmetry such that we can have finite temperature dome. From that result, we already know this superconducting dome energy scale need to be bandwidth energy scale.
But do you have an analytic way of describing the finite temperature?
No, unfortunately not. But we know from zero temperature, in the exact flat band limit, the transition TC must be zero. Which means when we make the band not flat, gradually increase bandwidth, TC should increase gradually, not immediately jump to some very high temperature.
How does the phase correlation then depend on temperature as you approach zero temperature in that model?
You mean for the
Yes.
exact flat band?
Yes.
That is actually a good question. That's a good question. I think it should be an essential singularity. It's an exponential decay on any kind of temperature.
Right.
Only at zero temperature.
How does the correlation then depend on the temperature? You have a rough idea of that?
Right. So if we go to thermodynamic limit, it will be zero. Exponential decay everywhere here.
Yeah.
And
Is it, for example, like a 2D Heisenberg model or something like that? Or?
this is actually a 2D. Yeah, this is 2D Heisenberg. This is 2D Heisenberg.
So it may have exponential of 1 over t.
That's right. Yes. Yeah. Because of SU2 symmetry, it's the same as the 2D Heisenberg. The universal class is the same.
I see.
The superconducting state is actually the ferromagnetic state of the Heisenberg state.
And so does the finite bandwidth reduce the symmetry to U?
To U1.
I see.
That's it. Because U1 charge is always there.
And do you
It's
explain
this exact flat band limit gives additional SU2
this is
emergency.
explained in your
That's right.
Yes, okay.
That's right.
We'll read it.
So from this SU2 symmetry argument, we know for sure, qualitatively this would happen. Just a number needed Monte Carlo to calculate.
Okay. Thank you.
Just clarify, when you say exact solution, this refers only to the ground state. You don't know the exact.
So actually, we know exact states, and we can calculate the Green's function for fermion Green's function.
But when you do when you know all excited states,
Oh, not all states. We know single particle excitation.
I see. Okay.
Not
I see.
But and I should emphasize that before our study, flat band Heisenberg model attractive interaction has been proved to have exactly the same figures. So what our new ingredient here is we generalize the potential from the Heisenberg on-site attraction to arbitrary distance attraction. which is important for twist barrier, because in twist barrier is not a Hubbard model. One can't expect it's unsightable. So, but we show that even if it's not unsightable, the same stuff actually works.
Just very quickly, is this essentially the same as Nagaoka state? It's effectively zero kinetic energy, and you're diagnosing the interaction.
Oh, you mean at the exact flat band?
The exact flat band.
I think that's probably,
Yeah.
I think you are right. I think you are right.
Yeah.
Yes, yeah.
We also have one last question, just about the Roton, which is so low.
Yes.
Does it have implications on the edge states? Is there some particular reconstruction that you expect?
Oh, that's a good question. That's a good question. Probably not, in the sense that in the experiments, they always do the temperature much lower than the Roton gap. Because if the temperature hit the Roton gap, the Roton excitation will ruin the on top, make it a compressible state. So because the temperature is always much lower than the Roton gap, the edge state cannot really see, does not really know the existence of everything. That's my expectation. I don't know for sure. That's my guess.
Okay. More urgent questions? So tradition this meeting to discuss the rest of physics over a beer, like one hour.
But I just make it, one last, can I encourage all of you, if you can, to come to the public lecture on Wednesday?
Do we have to do something for this? Do we still have to-
Well, yeah, we would like to know numbers, so if you could register at the Eventbrite event, if you're gonna come. Don't do it if you're not gonna come, because I'll give it a false. Be lovely to come. Thank you.
Okay, and then not.
No, it's gonna be imperial.
It's going to be interesting. Okay, so let's thank Kai-san again, and all the speakers. Session is closed.